Welcome to the walkthrough of Assignment 1 Part B for my CS5254 course in the summer of 2023. The objective of the second part of this assignment is to learn how to synchronize Java threads via a semaphore and a spin lock. Videos describing Java semaphores appear here and here. Likewise, a video describing spin locks appear here. I recommend you watch these videos to ensure you understand these Java synchronizers. Naturally, we'll cover these topics in class as well. In the second part of this assignment, you use a semaphore and a spin lock to enhance the multi-threaded implementation of the Palantiri Simulator app from Assignment 1A. Assignment 1B focuses on the PalantiriManager, which is used to restrict the number of beings from Middle-earth who can concurrently gaze into a fixed number of palantiri. If you're not yet a fan of Tolkien's Lord of the Rings trilogy, you should drop everything you're doing and read about palantiri here. The Palantiri Simulator app is packaged as a project using the latest version of Android Studio. This app is written in both Kotlin and Java and demonstrates many Android capabilities. For the purposes of Assignment 1B, however, you just need to focus on the following three folders. The Simulator Manager's Palantiri Spin Lock hash map, which contains the skeleton you need to fill in, as described below. App Source Test, which is a set of unit tests that exercise many Palantiri Simulator features and can be used to help test the functionality you implement for the assignment. And App Source Android Test, which is an Android Studio instrumentation test that runs your app automatically. To compile this code, you'll need to use the provided Android Studio project. You can run this project by clicking the green Run App button in the Android Studio IDE, which should automatically select an Android emulator to run, assuming you have one created. The app is designed to work with Android API level 33, so you need to select an emulator that uses API level 33. If you don't already have an emulator created, you can create it by clicking on the AVD Manager button in the Android Studio IDE. In addition to integrating the updated runnable threads manager.java and simple being runnable.java files from your Assignment 1A solution, you'll need to modify several files containing the skeleton Java code by completing the to-do you fill in here tasks to provide a working solution. Don't change the overall structure of the skeleton. Just fill in the to-do tags and do not delete the to-do tags. In particular, you'll need to finish implementing the following to-do tasks for this assignment in the spin lock hash map folder. For spinlock hashmapmanager.java, you'll need to complete the to-do tasks in various methods to implement a PalantiriManager via a semaphore, the appropriate type of spinlock, and a hash map. For spinlock.java, if you're taking this class for undergrad credit, you need to complete the to-do tasks in various methods to emulate a compare and swap style spinlock with non-recursive semantics. For the grad version, if you're taking this class, you need to complete the to-do tasks in the reentrant spinlock.java file in various methods to emulate a compare and swap style spinlock with recursive semantics. You'll also need to update the student.kt file to change the to-do tasks at the type field to either graduate or undergraduate, depending on which version of the assignment that you're implementing. Your app will be considered correct if it passes all the unit instrumentation tests and all beings successfully complete all their n iterations. A correct simulation should restrict the number of gazing beings to the number of palantiri. In other words, if there are 4 palantiri in the simulation, then only 4 beings should ever be gazing on the screen at any one given time. When the simulation is running, the app view will display visual feedback to show palantiri and being states, as well as the progress of their gazing iterations. If your assignment implementation is correct and doesn't throw any exceptions, then the app title bar labels will appear green when the simulation completes. However, if your solution is not implemented correctly or throws an exception for some reason, then red title bar labels will be displayed when the simulation completes. Graduate students, or students who are taking this class for graduate credit, must perform the following additional tasks. Enhance the spinlock hashmapmanager.java file to use Java functional programming features, such as method reference and/or lambda expressions. Likewise, if you're familiar with Java streams, please feel free to use that framework in your solution. Undergraduates are welcome to implement these features and methods, but it's not required. Skeleton code for this assignment is available from my GitHub account. Now that you've set up your GitLab account, you can pull the skeleton code into your repository, read it carefully, and complete the to-do markers. The additional work required by graduate students is clearly marked. Unit tests in the App Source Test folder are provided to increase our confidence that your implementation is working as expected. It's essential that you use the Android Studio GUI to run these unit tests locally on your computer, as described here and shown later in this video. As usual, testing only demonstrates the presence of bugs and not their absence. So don't rely solely on the test to detect problems in your code. In particular, I'll also provide videos that walk through frequently made mistakes that you should address. Please address these issues prior to your submissions to streamline our programming assignment review and assessment process wherever possible. This assignment is designed to help you get familiar with writing multi-threaded programs using the Android Studio IDE and core Java synchronization mechanisms, which complement the core Java multi-threading mechanisms covered in Assignment 1A. It doesn't require you to program with more advanced Java synchronizers or any advanced Java and Android concurrency frameworks, which we'll cover in upcoming assignments. Now that I've given you an overview of the assignment, let's drill down on the various skeletons you'll need to implement. These skeletons all reside in the Managers, Palantiri, SpinLock HashMap folder. We'll start with the SpinLock HashMap Manager class, which everyone needs to implement. This class extends the PalantiriManager and uses a SpinLock, a Semaphore, and a HashMap in order to be able to restrict access by many being threads to a fixed number of palantiri. You'll have to provide a field that is used to implement the SpinLock. This SpinLock, in turn, will be used to ensure that threads serialize on the critical sections we'll look at below. There's two different SpinLock implementations. One, which is the SpinLock class, which undergrads have to implement, and the other is the reentrant SpinLock class, which students taking the class for grad credit have to implement. In either event, you need to define an instance of that here as a field. You'll also have to define a counting semaphore that limits the concurrent access to the fixed number of available palantiri that are managed by the PalantiriManager. I provided you an implementation of a palantiri map, which is a hash map that associates the palantiri key to a Boolean value that's used to keep track of whether the key is available. You'll see how that gets used in just a moment. There's a hook method called back called build model that's called by the framework. And this is used to initialize the various fields we just described. So we go ahead and make a new hash map. And then you'll have to call the getPalantiri factor method and use the result that comes back to that in order to be able to initialize the palantiri map with the appropriate values. You'll also have to initialize the semaphore to use a fair implementation in order to mediate concurrent access to the given palantiri. And finally, you'll have to implement the SpinLock field. So those are fairly straightforward things to do, but you have to think through how to implement a fair semaphore. That's probably the thing that'll take little doing. Down here is the acquire method. This method is called back in order to be able to acquire a palantir, and it's intended to block until one is available if there isn't one available right away. So the way this works under the hood is you'll use the semaphore in order to uninterruptedly acquire a palantir, or rather, let me rephrase that, in order to wait until there's a palantir available. And then you'll use the SpinLock in order to ensure that only one thread at a time can actually come in and check the hash map to find the first key whose value is true. And this, of course, has to be done with the lock held so that you don't end up having race conditions when concurrent threads would update and access the hash map simultaneously. Once you found a free palantir in the hash map, then you need to set its value to false to indicate that it is not available. And then that palantir will be returned to the client and you'll release the SpinLock. All the code I just described needs to go here. There's also a little check, sort of a sanity check at the bottom of this method that will throw an illegal state exception if something went wrong. So make sure that you return properly, and if things go awry, make sure you go down here to throw this illegal state exception. Here's the release method. The release method is, of course, the inverse of acquire. It's intended to return the palantir back to the PalantiriManager, so it's available for other beings to use. And the way this works is the palantir is passed back in. You'll need to be able to use the SpinLock in order to make sure you have exclusive access to the hash map. Go ahead and change the value in the hash map, set it to true, saying it's now available for reuse. And then you'll release the SpinLock. And then you'll also go ahead and increment the semaphore to indicate that there's now a possibility for another thread to go ahead and get access into the PalantiriManager if there was a contention for the number of beings that were currently gazing with the limited number of palantiri. So those are the methods that you have to go ahead and implement. Here's a little hint. I call the field M available palantiri. That's just the name that I used up here when I defined this. You could call it something different if you wanted to, but that was what I happened to call it. So probably wouldn't be a bad idea to use the same name. It's currently colored in red because I have taken that definition out, so you'll have the fun of figuring out how to do the implementation yourself. Let's go take a look at the skeleton for spin lock. This is what the undergraduates have to implement. So the spin lock is used to emulate a compare and swap style spin lock with so-called non-recursive semantics. That means that once a thread acquires a lock, it cannot reacquire the lock unless it releases it first. The way you're going to do this is you're going to use something called an atomic Boolean, and that has a method called compare and set. And the default state of the spin lock should be unlocked. So you'll have to go ahead and define an atomic Boolean with those properties set here. There's a method called try lock, which is used to do a non-blocking acquire. So you'll have to go ahead and use the atomic Booleans compare and set method correctly here to do that check. The main method that you'll use is the one that's called lock. This is the one you have to implement. This is used to check to see whether or not the whether the lock is available. And if it's unlocked, then we're going to atomically lock it and then return. If it's already locked, we're going to continually spin, waiting for another thread to release that lock. So that's where you're going to have to use the atomic Boolean compare and set operation in order to do that. And there's a method, there's a field called mOwner, which is what I called the atomic Boolean. So I called it mOwner for lock owner. And this describes how you'll need to do this. You'll need to have a loop here that keeps trying to atomically set the value to true. And you should also, each time you try and fail, you should also check to see if a shutdown has been requested. And if it has been requested, then you want to go ahead and throw a cancellation exception. So you're going to check to see whether cancellation has been requested, and if so, it'll shut it down. Unlock will simply atomically set the Boolean to be false. In other words, it's now available for use. So you'll have to do an atomic operation. Of course, everything on the atomic Boolean is atomic, but you'll have to call the appropriate method to set the value of the lock to be false, which means it will be released. So we'll talk about how spin locks work in class, but these are basically the things you'll have to implement in order to make this work properly. Let's take a look at what the grad students have to do. The grad students have to implement a spin lock that has so-called recursive semantics, which we call reentrant. So a reentrant spin lock is like a spin lock, but it has this reentrant property. And all that means is that if a thread currently owns the lock, then it can reacquire the lock, simply incrementing a recursion count without having to release it first. So it makes it recursive. So basically, what you're going to have to do here is define an atomic reference that's used as the basis for the atomic compare and swap. And the default state of the spin lock, of course, should be unlocked. Now, the way you're going to do this is we're going to actually keep track of the thread ID that's the current owner of the lock. And so you'll have an atomic reference that's parameterized by thread. You'll also have to define a field that will count the number of times the owner thread has recursively acquired the lock. And so it just has to be a simple count, nothing fancy here. You can use an int, for example, as long as you give it the right default value. Over here, you have to implement the try lock method. This is the one that's used for non-blocking acquisition of the lock. And what you'll have to do there is fill in the value to basically try to set the owner's value, which this is the owner of the reference, to the value of the thread, which is considered true. And this will succeed if and only if the current value is null, which indicates false. So that's just sort of a one-liner. Down here is really the workhorse method. This is the lock method, similar to the one that the undergrads have to implement. The main difference here is that you'll have to get the current thread, and then you'll use the thread reference in order to be able to try to set the value of the atomic reference to the current thread reference. And that thread reference, of course, will be non-null. And so you'll have to keep checking to see whether or not you can atomically do compare and set to set the value of the atomic reference to the thread reference and then check to see whether it's null. So you'll have to figure out how to do that. Once again, you'll have to check each time you fail to do the set atomically, when you fail to get the exclusive access, to check to see if you've been canceled or not. And then if you haven't canceled, you have to throw a cancellation exception. Unlock simply goes ahead and sets the value back to null, the value of M owner, which is the atomic reference, back to null, but only if the recursion count is going to be equal to 0. If the recursion count is greater than 0 and the calling thread, the thread that calls on lock, is the one that currently owns the lock, then simply the recursion count is decremented by 1. So only when the count is 0 and the calling thread is the thread that owns the lock will we atomically release the lock that's currently held by the owner. So those are the various classes you'll have to implement in order to be able to do this part of the assignment. The key thing you'll be learning here again are semaphores in order to be able to mediate access to shared resources concurrently, as well as spin locks, which are used to guard critical sections from simultaneous access in order to be able to prevent race conditions. Now that we've walked through the specifications and the skeletons, it's time to turn our attention to the unit tests. If you go to the Android Studio project and click on App Source Test, and then right-click on Java, you can select the menu item Run Tests in Java. And that will cause Android Studio to go ahead and build and run the various unit tests that we've configured for assignment 1B, which also, of course, includes all the unit tests that we had for assignment 1A. As you can see here, there are 37 tests. My implementation, no surprise, passes all the tests. If all the tests pass, you see the green check marks. If something goes wrong, you'll get some indications. It'll either be orange or red. If that happens, then please go ahead and take a careful look at what's happening and see what you can do to fix the problems. Naturally, if you have any problems whatsoever that you don't know how to fix yourself, feel free to come to office hours and/or post questions on Piazza. As the projects go along throughout the semester, as we have more assignments, you'll have to continue to pass all the previous unit tests. And that's important because we'll often add new tests over time as we get better insights into how to automatically check to see whether or not the implementations that you're providing actually implement the specifications correctly. After you run the tests, please make sure you take a snapshot of it using screen capture software and include it in the top level part of your assignment 1B folder under some name like results.png or results.jpg so I can take a look and make sure your tests are passing. Now that we've shown how to run the unit tests, let's show how to run the instrumentation tests. To do this, you go into App Source Android Test, and then you right-click on Run All Tests. As you can see here, that goes ahead and compiles the code, and it'll load it into the emulator. If you don't have an emulator that's already up and running, it may take a few minutes or a few seconds, depending on how fast your machine is, in order to be able to launch the emulator. But once it's launched, it'll start out by showing the screen here that demonstrates all the different palantiri and all the different beings that are gazing. In this particular case, you can see that we've got 10 beings and 6 palantiri, and we're going to be doing 10 iterations per being. And you can also see what's happening. It's rotating the screen and kind of putting the test through a tortuous path to make sure it's working properly. As you might expect, if you have bugs in your code, either in the thread side with the thread manager or the Palantir side with the PalantiriManager, things are not going to work the way you might want them to. The tests run twice. The first time they run at, quote, normal speed, and the second time they run at sort of supersonic speed, as you can see here, just giving you more of a torture test type behavior. So if all goes well, you should end up with all the text at the top of the screen being a nice bright green. If you don't get bright green, then that is an indication that something is wrong.